Hey guys, thanks for joining me for this Unit 1.15 unit test review. This is my second time doing this, so hopefully it will go better and maybe not quite as long as the first time. Our goal today is to review for the Unit 1 test. And I don't want this to be a question for question review, so I didn't set this up so that each slide is one of the questions you're going to see. Instead, I really want this to be more of a just review of what we learned, and there will be some questions that are the actual questions on the test. I went ahead and put in my trick questions as I've been doing for the quiz reviews, and also we will do some questions that are like the ones on the test, but I'm not going to say first question, this is what you're going to see, and things like that. Okay, so here we go. Data versus probability distribution histograms. Okay, a lot of vocabulary here. I want you to be aware of this vocabulary that you're going to run into, the vocabulary and this tool. This is a particular type of tool called the histogram. Histogram is just a bar graph, and it's a way to display data, but I want to show you here just this compare and contrast. We have two bar graphs, two histograms, and one of them is showing us the data. So that's the one on the left. Here we go. We have red, yellow, green, blue, and then each bar shows us how much of each. So maybe this is that one with the marbles. It's 2 red marbles, 2 yellow, 2 green, 2 blue. But recognize that the numbers here are how many of each we have, not the probability. And we could figure out the probability by taking the data off of this histogram, right? There's two of each, and so there's a total of 2 plus 2 plus 2 plus 2, so there's a total of 8. So the probability of red is 2 out of 8, which is 1/4, which is 25%. And the probability of yellow is the same, 2 out of 8, which is 25%, and so on and so forth. So the probability histogram would look a lot like the data histogram, except that each bar would be at 20, whatever 25% is, 0.25, 0.25 on a different, it'd have to be a different chart, because this one, the y-axis, is numbers of marbles or amounts of whatever it is, and it's not displaying the probabilities. Okay, and then the second chart is, again, is a probability histogram. We're going to see a lot of these. We'll see lots of different types of them, but notice that this one, the numbers represent the probabilities of getting that, whatever it is that we're counting, that object or that number that's coming up. So maybe this is an 8-sided die. That's a bad example. This is the number of socks lost in the laundry each day, each load. And so the probability of not losing any socks is only 2% there, and the probability of losing 1 sock is also 2%, but the probability of losing 7 socks in a single load, that's really high. That's 18%, and if you ever do any laundry, you know that's true. Okay, so 2 different kinds of histograms. You're going to see both, so just get ready for it. Okay, moving on. Here's just a regular old question. This is, and it's actually 3 questions. This is nice. I gave you 3 questions here. I gave you 3 questions because I want you to see the differences. And so as we start talking about this, let me give you a piece of advice. When you are watching these recordings, you should not be sitting there eating popcorn. Okay, you can eat popcorn, that's fine if you have any, but you should not be passively watching me make a fool of myself on here. You should be actively trying to do the problems. So right now, put down the popcorn and hit pause and try to do these questions. Just try to puzzle them out. Just the first one. Just try to do the first one. See if you can figure it out. Then hit play and watch me do it and see if you and I are on the same page. And if we're not, you will learn much more effectively from what I show you than if you're just passively watching and eating popcorn. Okay. Use the probability distribution table to answer these questions. There's 3 questions here. I also have a mouse somewhere. Okay, there it is. The 3 questions are all asking what is the probability of this. And so let's just read this, the first one here, P, that means what's the probability, parenthesis, of this thing, and then inside the parenthesis we have an X, and that is the thing we're describing. So what's the probability that X meets this description? And the description is it's bigger than 2 and smaller than 5. That's what the 2 and less than sign means. 2 is less than X, or X is greater than 2, and X is less than 5. So what's the probability that X is bigger than 2 and smaller than 5? And of course, you know from the chart what numbers are both bigger than 2 and smaller than 5. I hope you're screaming at the screen. It's 3 and 4. So the probabilities that X is bigger than 2 and smaller than 5 are the possibilities are just 3 and 4. Well, the probability of 3 is 0, so that would be the probability that, another way to say this would be, what's the probability X equals 3 or X equals 4? That's what that question is asking. It says it in terms of greater than and less than instead of saying equal to, and that's fine. And we know that an OR probability like this can be figured out by doing individual probabilities. Probability of 3 plus the probability of 4. So what's the probability of 3? I hope you can see on the chart, the probability of 3 is 25%, and the probability of 4 is only a measly 5%. So the probability of both things is 25% plus 5%, which is 30%. So the answer to the question, what is the probability 2 is less than X, which is less than 5, is 30%, or 0.3, or 3/10, but you won't see that. So 0.3 is probably the best answer, since that's the form that all of our probabilities are given to us in the chart. Okay, now that you understand that, maybe, if you don't, rewind, watch again. Now that you understand that, try the next one. Hit pause, try the next one, hit play, see what I do. Okay, next one says, what's the probability that X is greater than or equal to 3? So in this case, the equal to bit means we're going to include the 3. Remember when it was less than a 5 or greater than 2, we didn't include the 2 and the 5. Now that it says greater than or equal to, we include the 3. So we're going to include the 3 and all the numbers bigger than 3. So 4, 5, and 6. So we're going to add up all of those probabilities, and I'm not going to bother to write down that this is the probability of 3 plus the probability of 4, and so on and so forth. I hope you can see that that's what's going on here. So it's 0.25 or 25% plus 0.05 or 5% plus 0.35, which is 35%, plus 0.10, which is 10%. Add them all together and you get 75%. And that is the probability that one of your selections, the X, when you select X randomly from this choices, is going to be a number that is either 3 or 4 or 5 or 6, bigger than or equal to 3. All right, one last time, hit pause, see if you can do the last one. Now the last one looks an awful lot like the first one, so am I just repeating myself? Why is it, what makes it different? Okay, so let's see if we can find the eraser here and erase what we've got going on here. So remember, when we did this first one, we said that X is greater than 2, so it could be 3 or 4, and so on, or less than 5, so that would be 3 and 4. Those are the only numbers that fit that description. But this time we're saying P is the probability of X being greater than or equal to 2 and less than or equal to 5. So we're including the 2 and the 5. So we're adding to what we count in here by including the ends, the numbers on the boundaries, which are the 2 and the 5. And so now we have to add the 4 probabilities. 15% plus 25% plus 5% plus 35%. Let's see, that's 40 plus 40 is 80%. So 0.8 or 0.80 if you like, but that's good enough for us. Okay, that's an important lesson in combining probabilities. Probabilities of a bunch of things happening is just the probability of each thing all added together. Probabilities of one of several things, I should say. Okay. Now, one of the cool things that you get to do in this test is you get to try to answer questions using something more creative than just picking A, B, C, or D. So you'll have a little bit of multiple choice, but you're going to have a lot of other stuff. Fill in the blanks is one. Write in the type of the answer is a big one. Multiple choices where multiple choice where you get to choose more than one answer is correct. And then this cool question, which I can't demonstrate for you on the board, but you'll know what I'm talking about if you've done the practice. If you've done the practice problems, you will have found a problem or a couple of problems where they give you this histogram. They set up this histogram for you, but instead of having a bunch of bars that are already there, it's just a bunch of little stubs. And then the stubs, the little bits of a bar, are movable, and so you can grab onto those bars and you can move them up or down whatever height they should be. So that's what we're going to do. We're going to bring our mouse down, we're going to grab onto one of the bars, just put the mouse on one of the X's, grab it, and then move it up as high as it needs to be in order to match what it should match here. So the question is saying, create a probability distribution histogram. Okay, we talked about that on the first slide, and the chart we have here is not a probability distribution histogram. It is the raw data. And I want to point this out. On the test, there's a mistake. Maybe when you take it, they'll fix it, but I doubt it. On the test, there's a mistake where they got the X and the F mixed up. So the F should be up here, and the X should be down there. I don't know why they even did that. So this is, maybe I'm wrong. I don't know. I think I'm not. I think I'm wrong on that. You know what? I think I'm thinking of a different one. Just ignore me. Wow. I said I was going to do a better job here, but I'm not seeing it. Okay. Here we go. Let's just pretend that never happened. Okay, so the X is the values that we're counting, so ones, and then the F is it's the frequency table, and I'm thinking of a different slide, and we'll see it in a few minutes maybe. Okay, so the X is the things we're counting, and that would be 1, 2, 3, and 4, and then the F is the frequency. Okay, so this is a frequency table, but we're not supposed to make a frequency histogram. So we're not just supposed to transfer this data onto a histogram. Instead, we're going to make a probability distribution. So we're not going to just move each bar up to the number that we see below it. No, we are going to do a probability distribution, which means we add up all the numbers, all the frequencies. 5 plus 7 plus 2 plus 9 is, I think, 23. Is that right? Yeah, I think that's 23. Okay, that's the total. And then the probability for each one is just the amount of the frequency of that thing, so how many ones, divided by the total number of things, which is 23. So the probability of 1 is 5 divided by 23. And we can do that on our calculator, which I need to pull up on my phone because I don't have access to my screen. So 5 divided by 23, do it on your calculator, is 0.217. So it's approximately 22%. And then the 2's, there's 7 of the 2's, so 7 divided by 23, and that's 30.4 or 30%. I'm just rounding it to the whole numbers. The 3's, there's only 2 3's, so 2 divided by 23 is 8.6%, or I'm going to just say 9%. And then 4's, there's a bunch of 4's. 9 divided by 23 is 39.1%. I'll just say 39%. Now notice this. All of those percents should add up to 100 if we did this right, if we if they don't, we did something wrong. 22 plus 30 is 52, plus 9 is 61, plus 39 is 100. Wow, it came out perfectly. Even though we had some rounding going on, the different roundings up and down balanced each other out, and we're left with a perfect probability distribution, more or less. And then to create the histogram, all we have to do is make each bar be as tall as it should be. So I'm going to say 10, 20, 30, 40. Okay, and that should be 0.1, 0.2, 0.3, and 0.4. Those are probabilities. So the first one should be a little bit more than 20. The second one should be up to 30. The fourth one should just be this little stubby thing, not even all the way up to 10. And the last one should be almost to the top, the tallest bar, almost all the way to 40. So we calculated our probabilities first, and then we were able to set the height of our bars for a probability histogram, because the data we're displaying on the histogram is different. It uses, but it's different than the data in the frequency table. Okay. That was a good one. Let's move on to the next. All right, this is a really tricky question. Eduardo has a red. Oh, this is a trick question. This is actually one of the questions on the test. So you have a 33% chance of getting this question. You will get one that's exactly like this one, only it may be talking about slips of paper being added together, or it may be numbers on slips of paper being added together, or it may be talking about, I can't remember what else. But it's going to be like this, where he's randomly doing two different things, and then they're interacting either by adding or subtracting, in this case subtracting. So here Eduardo has a red six-sided number die cube and a blue six-sided number cube, and the faces of the cubes are numbered 1 through 6, so it's kind of like two dice. Okay, Eduardo rolls both cubes at the same time. The random variable x is not the number on either cube. It is the number on the red cube minus the number on the blue cube. So what numbers could he get, and how many different combinations are there? So here's what I'm going to do. I'm going to draw just this big old chart, and I need to fill it in with all the possibilities. So I'm trying to draw this as neatly as I can. It's not coming out very well, but you get the idea. Okay, so I'm drawing this chart. Oh, what I wouldn't do for a piece of graph paper at this point. And that's a good point. You should always have graph paper around the house. Comes in really handy. Okay, now notice that what I did is I made a chart that was 6 by 6. Okay, and the space I had was wider than it is long, so it's rectangles instead of squares, and that's okay. Okay, now on the left-hand side, I'm going to write down the possible results from the red cube. When I roll that red cube, it's numbered, one sides are numbered 1 through 6, so I could roll a 1, a 2, a 3, a 4, a 5, and a 6. Those are the possibilities. Okay, now what about for the blue cube? Let's use blue ink to show this. The possibilities I'm going to write across the top are also 1, 2, 3, 4, 5, going off my board, 6. Okay, now those are the possible values when you're doing this. Now let's put those values together the way that this describes, and what it says is every time he rolls the dice, he gets a red number on a red cube and a number on the blue cube, and he takes the number on the blue cube and subtracts it from the number on the red cube. So red cube minus blue cube, that's the setup. Okay, so let's do this. Let's just pick a square and just fill in the number that goes in that square, okay, or rectangle. So here I am. The number on the red cube for that one is 3. The number on the blue cube is 3. 3 minus 3 is 0. So the number in that square is 0. Okay, let's pick another one. I'm just going to go at random. Let's just pick this one right here. Hopefully you can see that. So the red cube is 5. The blue cube is 2. 5 minus 2 is 3. 3 goes in that square. Okay, let's do another one on the kind of the other end of the spectrum. where the red cube is 1 and the blue cube is 4. Okay, so you see where I am. I'm just picking random squares and filling in the numbers. When the red cube is 1, the blue cube is 4, we have 1 minus 4. Always subtract the blue from the red. 1 minus 4 is a negative number, negative 3. Okay, so hopefully you can see how this works. Now I'm just going to fill in the rest of the chart like really fast, one at a time. Okay, so when red is 1 and blue is 1, 1 minus 1 is 0. When red is 1 and blue is 2, 1 minus 2 is negative 1, and then negative 2, negative 3, negative 4, negative 5. And then when red is 2 and blue is 1, 2 minus 1 is 1. But 2 minus 2 is 0, and 2 minus 3 is negative 1, and so on and so forth. Negative 2, negative 3, negative 4. I hope you're seeing a pattern here. When red is 3 and blue is 1, 3 minus 1 is 2. 3 minus 2 is 1, 3 minus 3 is 0, 3 minus 4 is negative 1, and so on. And when red is 4 and blue is 1, 4 minus 1 is 3. And then we can keep on going down, right? 3, 5 minus 1 is 4, 6 minus 1 is 5. And we keep going to the next column, negative 1, 0, 1. See the pattern, 2, 3, 4. Right? And that 4 means 6 minus 2 is 4. That's what we put there, red 6 and a blue 2, 6 minus 2. Okay, the next column, negative 2, negative 1, 0. 4 minus 3 is 1, then 2, then 3. So we just keep on going. We're counting up, going down, and down, going to the left, or to the right. Okay, negative 3, negative 2, negative 1. 4 minus 4 is 0. 5 minus 4 is 1. 6 minus 4 is 2. Okay, keep going. Negative 4, negative 3, negative 2, negative 1. 4 minus 5 is negative 1. 5 minus 5 is 0. 6 minus 5 is 1. And if you haven't yet figured out what I'm doing, go back and watch this again, because this is really important. Otherwise, you have no clue what we're talking about. Okay, 4 minus 6 is negative 2. Then we have negative 1. And then we have 0. Now notice that this row of zeros is or this diagonal of zeros here, right? That diagonal of zeros, that's where the numbers were the same. So 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, and so on and so forth. So we actually have, that is the most common answer. There's 6 zeros. That's the most common answer. The highest probability result is going to be 0. Okay, but then there's all these other possible answers, and most of the numbers are repeated. There's a bunch of negative 1s, there's one less negative 2s, there's a few negative 3s, 2 negative 4s, and then only 1 negative 5. On the other side, when we're subtracting a smaller number from a bigger number, we ended up with the positive numbers. So a bunch of 1s, several 2s, a number of 3s, 2 4s, and 1 5. Okay. That's all our data. Those are all the possible ways to get numbers. Okay, how many possible ways is that? How many different ways can we roll 2 dice and compare them and get a red and a blue that are different? That's 6 possible ways to get the red, 6 possible ways to get the blue, for a total of 6 times 6, or 36 possible results. Now notice there's not 36 possible number results, right? It only goes from 5, 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4, negative 5. That is 11 different values that we can get, but there's 36 different ways to get those 11 values. Okay, so a total of 36 ways. So when we're doing probability, what could happen is one of 36 options. Okay, so that's how we're going to do probability. 36 different ways. And then the question says, what's the probability that x is going to be greater than or equal to negative 4 and less than 0? So now let's look at our chart and see how many different ways we have a number that is less than 0, less than or equal to 0, and greater than or equal to negative 4. So I'm going to just put a highlight down here between the zeros and the ones. We want the zeros, that's what we're looking for. Less than or equal to 0, not greater than, so we don't want the ones. And then we're going to put a line all the way around all the numbers that are between negative 4 and 0, including the negative 4s and the zeros. Okay, so I've really just highlighted that all in, and you can see that those are the numbers, the squares that we're looking to find. Those would be our successes. And so that's what, when we say what's the probability, we're saying what's the chances we're going to get one of those squares out of the 36 possible squares. So we add all these up. There's 5, 10, 14 plus 3 is 17, 18, 19, 20. There's a total of 20 squares that we want, results that we want, representing all those zeros and negative ones and negative twos, negative threes, and negative fours. So that's 20 out of 36, and then we just pull up our calculator and we say 20 divided by 36 is 0.555 repeating, so the probability is approximately 0.556 or 56, however you want to round it, or 56%. And just a quick note on rounding. Most of the time when we're doing work with probabilities and fractions turned to decimals, we are going to have to round. That's an expected part of this test. However, you do want to follow the instructions, because you're going to be filling in answers like just typing it in. It'll tell you what place value to round it to. Okay, let's try another one. That was the tricky question. Identify binomial distributions. There's going to be two questions where you're just looking at a list of things and saying which one is this and which ones are not. Okay, so which ones are this and which ones are not. So this question says, which of these are binomial distributions? And kind of by process of elimination, you'll know which ones are not. And here's how it goes. A binomial distribution has three things. Remember, the three things are set number of trials, it's binomial, so two things, which we call success and failure, right? There's one thing we're looking for. That's what X represents, the number of times this thing happens, and then the number of times that thing doesn't happen is the failures. Okay, and then the third thing we're looking for is same probabilities, equal probabilities. I'll just say percents. So set number of trials. Each trial needs to measure success or as a success or a failure, and there needs to be an equal number of the equal probabilities for each trial. The probabilities have to be the same. They can't change from trial to trial. Okay, so let's read this first one, see if it fits the bill. A spinner comprises 3 sectors. Okay, we're suspicious already. 3 sectors. So why is supposed to be measuring 2 things? Sector A covers half the circle. Sector B and C each cover 1/4 of the circle. Okay, we got a spinner. We've got a spinner, and I don't even know where I am. There I am. We have a spinner, and A is 1/2, and B and C are each a quarter, and you spin the spinner around, and we can definitely figure out some probabilities with that, right? John spins the spinner 10 times. 10 times, that is how many trials? So that is step number 1, 10 times. Second, the variable X represents the number of times the spinner lands on A. Okay, that is a success, landing on A, so then landing on B or C would be a failure. So that's 2 things. Lands on A, that's a success. Does not land on A, that's a failure, so that's cool. And then are the probabilities the same? Yes. Probability of landing on A every single time is 50%. Probability of not landing on A is also 50%, 25% plus 25% for B and C. And so this is a probability, a binomial distribution. This is a good one. Okay, so we're going to say yes. Okay, let's look at the second one. Students in an auditorium are chosen at random to go stand together on the stage. So we're just going to call up 10 students, one at a time. 10 students total will be chosen. The variable X represents the number of students who are boys. Okay, now this is pretty easy to tell. 10 students are going to be chosen. That's a set number of trials. We're going to do this 10 times. Draw 1 student at a time. Come on up, stand on the stage all together. That's number of trials is set, so that's good. The variable x represents one thing, which we're going to call success, which is the student who gets called up as a boy. And if the student who gets called up is not a boy, then that would be a failure. And again, that's not a commentary on boys and girls. It's just the language. We could have said success is choosing a girl. It doesn't matter. Works. It's the same thing either way. So success or failure isn't necessarily a positive thing. It's just what we're counting. So the successes are what we're counting, and the failures are what we're not counting. Okay. Then finally, are the probabilities the same? Now this is a little bit tricky, because as you call students up onto the stage one at a time, you're taking them out of the pool of possible choices. So let's just say you call up a student and it's a boy. Now the next time you call up a student, there's just a slightly less chance of calling up a boy, because there's one less boy in the group of students to be called. It might be a huge group of students. Probability may be very similar to what it was before, but it has changed. This is that deal where we say without replacement. If you don't replace the objects that you're selecting back into the pool, then the probabilities have changed, and it's no longer a binomial distribution. So we say, no, this is not a binomial distribution, and that's because different probabilities. Okay, and excuse my handwriting. Okay, moving on. Then we talked about continuous probability distributions, and we're not going to mess around with these. We're going to go straight for the jugular. Use the probability distribution graph to answer the question. Probability of x less than a equals 60%. What is the value of a? Now, this is how this works. This is a probability distribution, but instead of measuring discrete items and adding up all of their probabilities so they add up to 100%, we are measuring a continuous range of items. Okay, in this case, I think these represented minutes down there, but they could have represented inches tall, or any number of things that could be measured in increments. Okay, in very small increments. So from 5 to 30, these are the probabilities for those values, and they go up for a while and they come back down again, but the total probabilities altogether is 100%. And how do we know that? Well, we said in a continuous probability distribution, the probability of a range of numbers is the area of this graph of the distribution between those numbers. So the total probability, in this case we're talking about a triangle, so the area of a triangle is going to be 1/2 times the base times the height. So the whole triangle is 1/2 times the base. The base goes from 5 to 30, so 5 to 30. 30 minus 5 is 25. So each square is 5 units long, and there's 5 of them, so 25. Times the height, and the height is our probabilities, and the highest point on this rectangle, or triangle, sorry, is 0.08. 0.08. And so we get our calculator out and we multiply. 1/2, or 0.5, that's 50%, 0.5, 1/2. 1/2 times 25 times 0.08 equals, and it turns out, you try this, it equals 1, because 1 or 100% is what 1 means. Okay, so the whole triangle, the area of the whole triangle is 1 or 100%, so that's all the probabilities together. Okay, that's fine. That's like no big revelation. Everybody knew that already. Now, the question is saying, as we bisect this triangle, as we draw lines through the triangle and cut it up into spaces, let's just say that I drew a line here, and I say, what's the probability of going from 5 to 15, being between 5 and 15? Then that probability would be this area right here, and we could calculate what that area is by doing 1/2 times the base, whatever the base is, times the height, whatever the height ends up being on the chart here. And we can find the probability of our numbers being between 5 and 15, whatever it is we're counting. Okay, that's the way those work. Now, this did not give me a range of numbers. It didn't say, well, what's the probability from here to here? Instead, it gave me a probability, and it said there is some point on this chart where there's some point we were going to call A, where x is less than or equal to A, and the probability is 60%. 60%, which is over half of the triangle, right? Over half, right? 60%. But I have no clue where that point might be. So there probably is a way to do this, and you should probably go back in the lesson and learn it. But I'm just going to say, let's just take a look at this and say, okay, there's a triangle. It's not a perfectly even triangle. See how it's kind of tilted over to the side a little bit? So this left side is a little bit bigger than the right side. So I'm going to just say, well, maybe this half, if we drew a line right here, then the half on the left, which isn't really a half, is slightly bigger than the half on the right. Maybe that's 60%. And I'm just going to guess. Okay, this may not be the best way to do it. Maybe a better way. This is the way that I've got right now. So I'm just taking a wild guess. I'm going to go ahead and draw a line here, and I'm going to say, okay, I am guessing that this is 60%. Now, if I run the numbers and I find that it's more than 60%, I move the line over a little bit. If I find it's less than 60%, I'll move the line over the other way a little bit. But I'm just going to try this. Okay, so the area is 1/2 times the base. Now, the base in this case goes from 5 to 20. So 20 minus 5 is 15. So 1/2 times 15, off to a bad start. That's an odd number times 1/2. That's not good. And then the height is still the same as the original triangle. It's still 0.08. 0.08. And I just do that on my calculator. 1/2 or 0.5 times 15 times 0.08. And that equals, and it, no joke, this is the way it comes out, 0.6, which is 60%. So that, not really a half, that side of the triangle is 60%. The other side of the triangle is 40%. So all of the chances that are 20 or less, the probabilities all add up to 60%. So probability of having 20 or less is 60%. So A equals 20, because that's where we drew our line. Okay. So A equals 20 in this case. Okay, that was a hard one. That's a tricky one. I think it's probably the hardest one. Here is the second question that is a guessing, is it this or is it not this? Okay, this is the normal distribution. Remember, we talk about normal distribution. It fits into this kind of shape where the majority of the data is in the middle around the mean, and then there might be some that are a little bit that are below, that are smaller than the mean, and some are more than the mean, but not that many. Let's see if we can see an example as the first one is an example. So is this a normal distribution? The height of each student in the math class. Now, the more students in the math class, the better chance there is that this will be a normal distribution. But, you take a bunch of, 15, 16-year-olds, they're all going to be about the same height. Not going to be a whole lot of them that are 2 feet high. There might be somebody who's 2 feet high, but not that many. It's going to be a very small number of really short ones. And then there might be some, there might be one guy who's on the basketball team who's like 8 feet high or 7 feet high, but not very many. Most of them are going to be somewhere in the, 5 feet to 6 feet range. And most of them will probably be average around 5.5 feet, like the vast majority of them are going to be like 5.5 feet within, a few inches of that. So that's called a normal distribution, and so this is, yes, a normal distribution. Hooray. as long as there's a bunch of students so we can get a big sample. Okay, the number of babies born each month at the hospital. Now, if you think about it, that takes a long time to gather that data, right? Every single month you have to go down and ask how many babies are born today, how many babies were born yesterday, how many babies, you add them all up. So it's going to be a long process, but if you count this over years, it's a lot of data. It's not going to be all the same numbers. And one of the rules for a normal distribution is there has to be some variety in the data. It can't all be the same. So it's very unlikely that every single month the same number of babies was born. And it's very unlikely that, like, some months 3 babies are born and other months 50 babies are born. It's probably going to be closer to, like, every month it's about the same number of babies, but a little bit more, a little bit less. Some really odd months, there was a bunch of babies born, and there might be one month where there's just hardly any babies born. But for the most part, most months is about the average number of babies are born every month, give or take a few. Okay, so that is a good normal distribution as long as you gather the data for lots and lots of months. If it's just like 3 months, it's not going to be a normal distribution. It's got to be quite a bit of data there. Okay, how about the next one? Price of each item at the dollar store. Is there going to be a lot of variety there? In case you've never been, guess how much every single item in the dollar store costs? $1. So there's no distribution of values. There's no variety. Every single item is $1. And so if you do like a bar graph, it's just going to be 1 bar going straight up. It's every single item is $1. There's no other values. So this is not a good normal distribution. That's an example of no variety. All right, number of strings on each guitar in the guitar store. It turns out that most guitars have the same number of strings, right? Most of them have 6 strings. You might have 2 or 3 guitars that have 12 strings. And if you want to count the ukuleles with 4 strings, might count, although I don't think they're really called guitars. But that's it. And now that starts to look like a normal distribution, but there's just not enough variety. The number of strings on each guitar, there's only like 3 choices, and so it's not going to be a normal distribution because there's just not enough variety between the choices. There's only like three different choices. Okay, moving on. Calculating z-scores. Okay, we're getting close to the end. This is the second to last. Though I snuck in 2 questions here. This is from the practice. We're talking about z-scores, and when we talk about z-scores, we're also talking about the z chart. I'm sorry, I've completely forgot what it is, but let's back up a little bit. Okay, so when we have our normal distribution, wow, that was just complete awkward silence. So we have our normal distribution, and I shouldn't be trying to teach the whole lesson here. This is just a reminder. But when we have a normal distribution, this value in the middle is called the mean value, and it cuts the normal distribution in half. And then we talked about this thing called the standard deviation, and we gave it a little Greek symbol there, standard deviation. And so there's a value that's 1 standard deviation away, and then 2, and then there's a value that's 3, and we can go backwards. So there's 1 in the opposite direction, so that's negative, and 2, and 3. Okay, so we had this chart, and we put some percentages in here. So we had how much each area is worth in percents. But we found that was too constraining, right? So, for example, the one that we have on the board here, the mean is 68.3 inches. That's the number that goes right in the middle, and the standard deviation is 2.9. So the next number for this would be 71.2, and then one more standard deviation up would be 74.1, and so forth. Okay, and then we go down. 68.3 minus 2.9 would be 63.9, as 5.4, 65.4, and we can keep on going down to find more standard deviations away from the mean. And remember the way this is distributed, that within the context here, 16-year-old boys normally distributed in height, most of them are going to be around 68.3 inches tall. A few of them are going to be less than 65 inches tall, not that many, and really a very small amount are going to be less than whatever the next one is, 62.5. And a few are going to be over 71.2, and very few are going to be over 74 inches tall. So that's what this standard distribution means. Now, here's the thing. We have a chart, and it's in your notes, and I'm not going to recreate it here, that tells you what percent each of these areas is. But what if I want to find a percent that does not match up with these areas? What if I want to find a percent that's like not on the chart? And that's the situation we have here. I want to find the 94th percentile. I want to know what's the score at the 94th percentile in this normally distributed data. And so to do that, I have to I need to find a connection between the area that is 94%, and it's going to be a big area here. Most of this is going to be covered in 94%. I'm just going to pretend it's right there, but I don't really know what it is. So if all of that is 94% of the data, what number is this right there? What is that number? So in order to answer that question, we're going to answer a different question first. We're going to associate a different number, and that number is called the z-score. Now, you really want to go back and learn about z-scores again if you didn't get this the first time. But the z-score is how many standard distributions away you are from the mean, either in the positive direction or the negative direction. And the z-score isn't just a whole number. It can be a fraction, because like if the z-score is, if z equals 2.5, that means that your number is 1, 2.5 standard deviations away from the mean, away from the center. Okay? And if we know what the standard deviation is, then we can figure that out as long as we know what the z-score is. So how do we know what the z-score is for the 94th percentile? That's where we get out the chart. So I am very sorry. I'm going to have to kind of mess things up here. Let's see. I'm going to end this for just a minute and pull up my chart. And the question was the 94th percentile, and we have this chart. Here it is. This is the standard normal table chart. It's the z-scores. And we're going to look on this, but here, let me show you what this means. The first column is the z-score. It starts at -3, and it goes all the way down to +3, or all the way up to +3. And then the top bar is going to be the hundredths place in the z-score. So z-scores, again, can be fractions or going to be decimals. And so we have z-scores from -3 counting down by tenths, and then the going across the columns represent hundredths of z-scores. Okay, now let's go down to the 94th percentile. So within the chart, within all the rest of the squares, those are percents. So for example, right here, this is 4%, 0.0485. That's almost 5%. So now we're trying to find 94%. So we're going to go down here to the 90s, 0.9, 0.98, 0.95, 0.94, we're getting close, 0.9418, 0.9406, 0.9394. Okay, so this one is not quite 94%. This one is a little bit bigger than 94%. So which one are we going to go with? Well, this one is actually 6/100ths of a percent away from 94%, right? You add 0.0006 6, and you would get up to 94%. This one also is 6/100ths away. It's if you subtract 0.0006, you would be at 94%. So actually, the z-score we're looking for is like smack dab in between these. So we're just going to pick one. We normally we would go with the one that's closest, but and this was actually kind of a bad choice. We're going to have to pick one. So I'm going to just pick this one. And so we need to look across that line. And that's 1.5, so the z-score of 1.5. And then I'm going to go down the row, and the top number is 0.05. So it's 1.55. That's my z-score, 1.55. Let's go back to let's go back to this and keep displaying this. We'll go this way. Here we go. And where did we end up? There we are. Okay, so we looked on the chart. We found our z-score of 1.55. Z equals 1.55. Now, I know you're all just completely amazed by that. I found the z-score for our 94th percentile. So we found 0.94. It wasn't exactly 0.94. And we found that it represents a z-score of 1.55. Okay. What's the z-score associated with the 94th percentile? 1.55. There it is. Okay, second question. Round your answer. What is the 94th percentile? And that question is asking, okay, you found the z-score. What is the actual number that is 1.55 standard deviations away? And there is a formula that we use, and it's in the notes, and I have to admit I've been kind of making it up. So we looked at it today and found out the formula goes like this, and I'm going to give you the informal formula. So the raw data, the data point that we're looking for, which is the 94th percentile, the number at the 94th percentile, which is the number that's exactly 90, which is larger than 94% of the data, is equal to, here's the formula, the mean, okay, so I'm just going to use m, they use a Greek letter for mean, but I'm just going to use m, plus the z-score, and I'm going to use z, times the standard deviation, and we use this other Greek letter here that looks like this, and I'm not very good at drawing Greek letters, but it's kind of like that. And that's the symbol for standard deviation. Okay, that's how you get it. That's how you find that number, the raw data there, the raw score is the mean, which in this case, mean is 68.3, plus the z-score, which is 1.55, we had to use the chart to find that, times the standard deviation, which we were told is 2.9. And we just do that on our calculator. And if you have a good calculator, it should tell you, or it should do the order of operations correctly. So 1.55 times 2.9, and then plus 68.3. That's the order you should do things in. Plus 68.3 equals, and you get a number that's equal to 72.795, and we'll round that to the nearest whatever place value our data is mostly in. It's mostly in tens place, so I'm going to say 72.8 inches. And so 72.8 inches, which is just above the first standard deviation, a little bit halfway between first and second, is the number that is bigger than 94% of the data in this distribution. Crazy, right? Okay, let's do the last one. This is it. This is an actual question from your test, or very like one. Let's do the whole thing again, and this time I'm probably not going to show you the chart. Use the chart to find the indicated area. And oh, when I say area, remember that that distribution thing. This is a probability distribution. So when we find the area of a section of it, the area is also the probability. The probability and the area are the same. Remember that the whole thing with the area of the triangles, we're talking about the same thing. These probability distributions, you find the area, that is also the probability. Okay, so the masses of eggs collected on a farm are normally distributed with a mean of 55 grams. Mean of 55. Standard deviation of 4.2 is the standard deviation. Approximately 80% of the eggs on the farm have a mass greater than what mass? Okay, now 80%, think about that, that's a lot. So change our pen color here and we'll see if we can mark off what we think is 80%. 80% is a big amount, and greater than would be over here. Okay, so that's 80%. So there's a number here that is the number of the mass of an egg where 80% of the eggs are bigger than that number. That's what we're trying to find. Okay, but that means that the rest of the mass, the rest of the eggs, 20% of the eggs are smaller than 20% are smaller than that number, and 80% are bigger than that number. Now, why is that important? Because our chart only gives us the smaller numbers, the less than percentiles. So it doesn't give us the greater than percentiles. It only gives us the less than percentiles. So when we look on our chart, we're not going to look for the 80% because the chart is telling us the z-score for the number that is greater than 20%, not less than 80%. Okay. So let's look on our chart, and once again I'm going to have to end the slideshow to pull up the chart here, and this time we're looking for 20%. So I have to scroll way up here to the 20%, and looks like, oh, I don't know, there's 20 and 500ths, there's 19 and 77 hundredths, so that's not quite as close to 20% as this one is. It's only 5 hundredths above 20%. So that's the one I'm going to use. I'm going to go across here to negative 0.8 and then up here to the 0.04. So it's negative 0.804. And we will resume the slideshow. Let's do that again. So my z-score, get my pen back out here, my z-score is z for number where 20% or less than is negative 0.84. I think that's what I said. So there's my z-score, and now I want to find out what that number is. Now again, the question said 80% are greater than, but my chart only tells me the z-scores for numbers with the percent that's less than that number. So that's why I had to use 20%. But it doesn't matter. The z-score for less than 20% is the same as the z-score for greater than 80% is greater than. And so now I'm going to find that number. Remember the raw data, the number is going to be the median plus the z-score times the standard deviation. Okay, so it's going to be 55 plus negative 0.84 times 4.2. Do that on your calculator, please. Notice that the z-score is negative, so we're actually going to end up effectively subtracting instead of adding our 0.84 times 4.2. Okay, and then we're going to subtract, and it's going to be negative 3.528 plus the median, which is 55, and that equals 51. 51.472. We'll round that to approximately 51.5 grams. So 51.5 grams is the number where 20% of the data is below that number and 80% of the data of the eggs are above that number. And that's all there is to it. Phew, that was a lot. This was an entire hour. Thank you so much for watching. And give me a call if you have any questions.